Alright, here's our problem. The allowable bending stress is 120 megapascal and the allowable shear stress is 130. In this problem, we are going to account for the weight of the beam. So the first thing I want to do is find the minimum value for section modulus. That's S. This equation should look familiar. Let's rearrange it for S. We are given the allowable shear stress here, but we just have to find the maximum value of moment here in our setup. It's cantilevered, so we know that the maximum moment is going to occur right next to the wall here. So let's figure out what that would be. I'm going to redraw our distributed load, and we find that the total weight is 75 kilonewtons. The math here, basically I'm just taking the area of this triangle. Half times this side times this side. And something to note here is that we're representing this distributed load not right in the middle of this triangle here, but 2/3 of the way to the heavier side. So there'd be only a half of a meter to the left, and then a full 2.5 meters to the right. And that distance is important, of course, because we need it to find our moment, which is force times distance. And it's time to start thinking about units. Our allowable stress is given in the units of megapascal, which is also newtons per millimeter squared. So I want to get our units of moment to be consistent with that. I've got to multiply by 1,000 to go from kilonewtons to newtons, and by 1,000 again to go from meters to millimeters. So we end up multiplying by 1,000 twice, which is 10 to the 6th. Oh, did I square millimeters? I did not mean to do that. That's better. But you'll see we put this value in for moment in our equation for section modulus. And we got our required section modulus. So here's the time where we refer to a table in the book, an appendix, or just go online to find a table that lists a bunch of types of beams and their S values. The table I'm looking at, it lists all the S values in values that are times 10 to the third. So it would be helpful to put this number as something times 10 to the third. There we go. So we're looking in the table for something with an S value of over 1,562. So I scanned the W-type beams, and the closest thing, without going under to 1,562, was all the way up at about 2,000. So that's substantially bigger than we need. So I went and looked also at the S-type beams and found something at about 1,600, which should be adequate, but not excessive. This is specifically that type of beam. This is its identification here, and its section modulus is given as that value. And there's also a lot of other information given, such as the mass per unit length. We're going to need that to find the weight of the beam and see how that adds stress. So the linear density is given in kilograms per meter, which we should point out is a mass per length, not weight per length. So we're going to need to convert to newtons, which we do by multiplying the kilograms by the acceleration of gravity, 9.8. So that's our linear density in more helpful units. So the overall number of newtons over these 3 meters remember we're working with a 3-meter long beam here, is that linear density multiplied by the length, 3 meters, and that should be the total weight of that 3-meter beam. But let's stop for a second and talk about why we're finding this information. We want to make sure that the weight of the beam along with the load on the beam doesn't bring our actual bending stress above the allowable value. So we're going to use this equation to make sure that in the end, with our moment that involves both the load and the weight of the beam, that our stress doesn't go above 120. So let's figure out the moment created by this, by this weight. We know that the weight is distributed over the length of the beam, but we could approximate that as being a weight that's right in the middle. So that would be 1.5 meters from the wall. Our moment is the weight times that distance, and let's put that in units of millimeters like we've been working with. And that is the moment from the weight of the beam itself. Let's go back and find the moment of the load. So this was the moment created by the load. So we have to add these two together to find the total stress. And that sum would look like that. And then we divide by S. And this is the actual section modulus of our beam, which we looked up in the table and found to be this value. So I plug that in there. And we get the actual stress. Is this more or less than the allowable? I don't remember. Let's check. The allowable is 120 megapascal. We have 113.6 newtons per millimeter squared, but remember, a newton per millimeter squared is also a megapascal. So we're coming in under the allowable stress, which is great. So even with the weight of the beam, we are in the clear. But we have one more thing to consider. We don't want to go higher than the maximum shear stress. So let's find the actual shear stress and compare that to the allowable. First, let's just get an idea of what the horizontal shear stress would be. So it's pretty easy to calculate an average value. So we have to figure out what is the biggest shear in our beam, accounting for both the distributed load and the weight of the beam. We already know the distributed load is 75,000 newtons, and we have seen that the beam itself weighs 3,058 newtons. So therefore, at the wall here, the total shear is going to be the sum of those two values, which is this many newtons. So we've got a V to put into our equation here. Now we have to figure out the area of the web of the beam. And a lot of tables will include this information, but the table I'm looking at does not. But it does have a lot of information. I think we can figure out the area of just the web based on other information that's there, such as information about the flange. We're given the flange width and its average thickness. So multiplying those values together should give us the area of one of the flanges. This would be one of the flanges here. 2,798 millimeters squared for one flange, and also the other. So if we take the total area and subtract the area of the two flanges, we're left with the area of the web. So here's the total area which is given in the table. We're subtracting one flange then the other, and we get an area for the web. And when we plug in our numbers in this equation, we get 10.3 Newton per millimeter squared, or 10.3 megapascal, and that is nowhere near the 130 megapascal that's allowable. So I'm gonna conclude we're probably can check off our horizontal shear stress requirement and conclude that this beam would work for us.